morning, everyone. I hope you're all doing well. We have 2 more weeks left, 3 more lectures, and our final exam is on next Thursday during lecture time, same as the first 2 midterms. Okay, so this week we're wrapping up rigid bodies, and then I'm hoping that on Tuesday we'll do some review, and I will do also a couple problems involving systems of rigid bodies or systems of particles and rigid bodies. So our progression in this course went as follows. We started with a particle, and we looked at the kinematics, then kinetics of a particle. We looked at the balance laws, the balance of linear momentum, balance of angular momentum. Then we looked at the linear impulse, linear momentum equation, angular impulse, angular momentum equation, and the work energy theorem. Same for a system of particles. We looked at the balance laws, linear momentum, and angular momentum, and then the impulse equations and the work energy theorem. So can anyone guess what we're going to do today for rigid bodies? We already introduced the balance laws. We did some practice last week. What are we going to do today? Exactly, the linear impulse, linear momentum equations, and we're going to also try to finish up the work energy theorem. So the linear impulse, linear momentum equations, angular impulse, angular momentum equations for a rigid body. Let me ask you this. Since we've already done this for a particle and for a system of particles, what is the linear impulse, linear momentum equation for a rigid body? Remember, how do we obtain the impulse equations from the balance laws? What do we do? Exactly, you integrate with respect to time. So that's what we're going to do. This is the balance of linear momentum. The linear impulse, linear momentum equation linear impulse, linear momentum equation, that's going to say that the integral of f dt from t1 to t2 is equal to g at t2 minus g at t1. The integral of f dt is equal to g of t2 minus g of t1. That's the linear impulse, linear momentum equation for a rigid body. Same for as for a particle or for a system of particles. That's the exact same form, except that for a rigid body, how is g calculated? How do we calculate the linear momentum of a rigid body? Exactly, it's the total mass times the velocity of the center of mass. Okay? Now for the angular impulse, angular momentum equation, for the angular impulse, angular momentum equation, we will have 2 forms corresponding to A and B above. We will not have a form C because form C is not easy to integrate, right? So I can easily integrate H dot O or H dot C using the fundamental theorem of calculus. Same for H dot P or H dot C, but this term is not easily integrable. I'm not sure if even we can write an expression for the integral of that. So we're just going to do the angular impulse, angular momentum equation. We're going to use it for A or B. So that would be the integral of MO dt. So the angular impulse is equal to HO at T2 minus HO at T1. About the center of mass, okay. So these are the linear impulse and momentum equations, angular impulse, angular momentum equations for a rigid body. So please take one and pass. Please pull up set 22s. the equations are pretty simple to derive, right? There are just the integrals of the balance laws with respect to time. Any questions? Questions? Based on your experience with the course so far, when do we use the linear impulse, linear momentum equations, angular impulse, angular momentum equations versus when do we use the balance laws? Or what is the difference between the two equations, practically speaking, when it comes to problems? Any ideas? Yes?
If you have a force that's applied for some time.
Exactly. So if I have a force that's applied over time, then what should I use, the balance laws or the impulse equations? Impulse, right. So if I want to relate two states or one system, two states of the system at different times, usually I'll use the impulse equations. So the balance laws are going to give us differential equations of motion. And if I want to relate two states, I'm going to have to integrate these differential equations of motion. The impulse equations relate two states. When is another case where I would use the impulse equations and for which I cannot use the regular balance laws? Remember we said once that the impulse equations are more general than the balance laws? Exactly, when we have impact, right? When we have impact, when the velocity, the angular acceleration, when the acceleration and the angular acceleration are not defined because the velocity and the angular velocity are not continuous, then we would use the impulse equations. Does that make sense? Okay. Let us open up our problem set 22, looking at the first problem. I'm going to try to sketch it on the board. So set 22, problem 1. Oopsie. Okay. Okay. A person who walks through the revolving door exerts a 90 Newton horizontal force on one of the 4 door panels. So here I call the force Fa. And keeps the 15-degree angle, I called it beta, constant relative to a line which is normal to the panel. If each panel is modeled as a 60 kilogram uniform rectangular plate, which is 1.2 meters in length, as viewed from above, determine the final angular velocity omega of the door if the person exerts the force for 3 seconds. The door is initially at rest and friction may be neglected. Okay, take a minute to read the problem again, come up with a strategy, chat with your neighbor, come up with a strategy to solve this problem. Any extra set 22s? They're there. Okay, so any ideas? So this person is pushing the door for 3 seconds in a certain way given. We need to find the angular acceleration or angular velocity, of the revolving door after the 3 seconds have passed, elapsed. What do we do? Any ideas? Yes?
I think the first thing is just to find the moment of inertia. That's how I would do first.
Okay, the moment of inertia of like the rigid body which is dependent about O, right? Okay, we can do that. Then what? Integrate the moment of inertia, like the inertia tensor.
Well, it starts from rest, so you know that angular momentum t equals 0 would be 0.
Exactly, the system starts from rest, so the initial angular momentum is 0.
And then at t equals 3, it's inertia times omega. So then that's the right side.
That's the right side of which equation?
The angular impulse and
Right, so we're going to use the angular impulse, angular momentum equation. For this system, the center of mass of the system is a fixed point, so they're the same equation. A and B are the same equation because C and O coincide. So we're going to use the angular impulse, angular momentum equation. Okay, so I will just write down the equation first. Integral T1 to T2 of MO dt is equal to HO. Okay, so I think that this equation makes sense to use. I've written it down. Now I need to evaluate it. Let's go through every term and see if I know what it is, if it's known or unknown, if I can calculate it or not. Deal? So I'm integrating between which 2 times? 0 and 3 seconds, right? MO. Can I calculate the sum of moments about O? Yes. Let me put a rotational basis on the door. How do I calculate MO? What are the forces acting on this door? What, the applied force F, yeah, and weight and some reaction force, but both the weight and the reaction force, they pass by through O, right? So they have no moment about O. So the only force that's providing a moment about O is what? The applied force. Okay, how do I calculate the moment of this applied force about O? R cross F, right? So what is R here? L1 EX cross the force FA, which is FA, and I have its direction too. What is its direction? What is the rotational EY component of FA? Cosine beta, right? What about the sine component, the EX component? Yeah, minus sine beta. dt. Okay, so that's the MO term, which I can calculate, right? What is the resultant of this cross product? What is EX cross EY? EZ, and the EX cross EX is 0. So I'll get FA L1 cosine beta EZ the integral of that from 0 to 3. What does this integral evaluate to? Yes, why? Yeah, it's constant, does not depend on time, so it's just 3 times FA L1 cosine beta easy. Okay, so that's the left-hand side of the equation, all done, all simplified. Calculated everything. Okay, now for the right-hand side, what do I do? How do I calculate the angular momentum of the system about O, HO? Yeah, I-O omega, right? I-O, well, let me write it down here. HO is I-O omega. Now in the special case where omega is along EZ, that will be I-O xz omega EX plus I-O YZ omega EY plus I-O ZZ omega EZ. That's if omega is along EZ, which is the case here, right? Is omega along EZ here? What is the direction of EZ? Perpendicular to the page, right? Out of the page. Omega is along EZ. Remember, this is a matrix. The inertia matrix, the omega matrix. And here, if omega is along EZ, then that's my omega. So if I carry out the matrix multiplication, I'll get this expression. Okay. What do I do next? Exactly. I need to find the inertias, right? I need to find IOXC, IOYZ. Sorry about that. Okay. So I need to find IOXZ, IOYZ, IOZZ. This I can find from geometry. What is the initial angular velocity of the system? 0, right? So what is the initial angular momentum of the system at t equals to 0? 0, right? So this term is 0 here. This is 0 because the system starts from rest here. So I'm left with the angular momentum at t equals to 3 seconds. And that's this where omega is what I need to find. Now, how do I calculate the inertias here? I'm not going to use the integrals. Right. So what is the shape that I have?
4 bars, 4 times.
Yeah, well, this is a top view, right? If I were to look at the 4-door panel, these are, you can think of them either as 4 rectangles or 2 big rectangles, right? That's what they are. So I'm going to use the parallel axis theorem. I'm going to use the fact that the moment of inertia of a system of rigid bodies or of a composite body is the sum of the moment of inertias of each of these bodies. And I'm going to use the tables. So let's open up the tables. Okay, so we can think of the revolving door as being composed either as a 4 panels, rectangular panels, or 2 big rectangular panels. And in both cases, when we calculate the moment of inertia, we should get the same answer, right? Let me use case B. Now, what is the moment of inertia? Well, let us first agree here that what are the products of inertia in this system? They're going to be 0 because of symmetries. So basically, all I need to calculate is IOZZ omega EZ. IOZZ omega at t equals to 3 seconds. Easy. This is what I need to calculate. If I have IOZZ, then I can solve for omega. Okay, how do I calculate IOZZ? So if I'm thinking about 2 plates, what is the moment of inertia of each plate about EZ passing by the center of mass? EZ is outside the page. Go ahead, look at your tables. Do we have a rectangular plate in the tables? Yeah, the first plate, but we're going to have to take the thickness to be 0, right? Okay, so what is the moment of inertia of each plate about its center of mass? What is it going to be? But what about for here, in this case? 112 ml squared, where L is L1 plus L2. Do we agree? Exactly, you have to take the full length, so 2L squared. Now do we agree? Take a minute, think about it, chat with your neighbor, make sure they're okay with it, and I'm happy to answer any questions. Yes. The z equals to 0 plane. Z equals to 0 plane is a plane of symmetry. So when you get to integrate the moment of inertia, for example, Ix is the integral of xz dm. For every point xz, you have a point x, or same z minus x. So they will go away, yeah. Oh. Yeah, here you have total symmetry. So x equals 0, y equals 0, z equals to 0 are all planes of symmetry. Yeah. So there are many reasons why the moment of products of inertia will cancel out here. Okay. Any other questions? Are we okay with this moment of inertia for each plate about its center? Yes. Why 4? Mm-hmm. What is it? Yes, okay. You're right. And then because I have 2 plates, I have 1 over 12 m 2L squared, right? That's if I'm considering the case B, 2 large rectangular panels. If I'm considering A, what is IOZZ? How do I calculate IOZZ for case A? I have 4 panels. Each panel had the length L, 1 over 12 ml squared. But I have to use the parallel axis theorem, because if I'm considering 4 plates, their center of mass is not at O, basically. So what is the term I need to add here?
4 times
L over 2 squared. Is that what you said? Do we agree? Think about it. Raise your hand if I should go over this. Okay, cool. So in case A, I'm thinking of 4 plates like this, composing the door. Each one has length L, right? Oh, I messed up the mass, by the way. So should I take M to be the mass of each panel? If that's the case, if M is the mass of each panel, then in the previous V, I should use 2M here. Okay. So IOZZ, this is O. The moment of inertia of this panel about O, you can find it from the tables. It's going to be 1 over 3 ml squared. And it's the same for all of these panels, so multiply by 4. Or you can also find in the tables that the moment of inertia of each of these plates about its own center of mass C is 1 over 12 ml squared. Plus, to find it about the end O, I have to use the parallel axis theorem, which would be adding the mass of the plate plus the distance between C and O, which is L over 2 squared. So these two are the same, because 1 over 12 plus 1 over 4 is going to be 1 over 3. Sorry. So this calculation is also the same as that one, considering the door as being composed of one big panel and another big panel. Now of mass 2m and length 2l. Now what's convenient about this is that the center of each panel coincides with the center of the system, which is the original. Where should I repeat? First of all, we'll be able to get this 1 over 12 or 1 over 3 ml squared value from the table. Yeah? Then, yes. What is it? That's the parallel axis theorem part, right? The parallel axis theorem says that IOZZ is equal to IAZZ plus M AX squared plus AY squared, where AX and AY are the components of the vector that goes from O to A. So the vector that goes from O to A is this one, 0 Y component. The X component is L over 2. So that's the L over 2 squared. That's where it comes from. The parallel axis theorem. Okay? Any other questions? Does that make sense? Are we done with this problem? We can plug in the moment of inertia we calculated, and we can solve for omega at t equals to 3 seconds. Okay? Questions? Questions? Okay, I'm picking up set 22 again. But before I do that, I want to ask you, under, in which cases is the, in which case or under what condition is the linear momentum of a system, of a rigid body conserved? When is the linear momentum of a rigid body conserved? Exactly, when the external forces acting on the system, they sum to 0, right? When this f dt term is 0, when this term is 0, then g at t2 minus g at t1 is equal to 0. G at t2 is equal to g at t1. So the linear momentum of the system is going to be the same. What about the angular momentum of a system about a fixed point O? When is it conserved? Yes?
Net external moment.
Exactly, when this term MO is 0. Same for the center of mass. Okay. Let's look at problem 4 in the set. Just after leaving the platform, so problem 4. Just after leaving the platform, the diver's fully extended 80 kilogram body has a rotational speed of 0.3 revs per second about an axis normal to the plane of the trajectory. Estimate the angular velocity and later in the dive when the diver has assumed the tuck position. Make reasonable assumptions concerning the mass moment of inertia of the body in each configuration. Okay, take a minute, think, chat to their neighbor. How do we solve this problem? Any conservations maybe? I don't think it's a sphere, it's more of a cylinder.
Yeah, it's more of a cylinder.
But which equation are you using though?
The angular momentum before and after has to be the same with a different moment inertia.
Why is angular momentum conserved?
Because he's not exerting, he can't exert any moments on himself.
Right, there are no external moments that are being exerted on the body. Yeah, that's right. Okay, so when is the moment of inertia of the diver about his own center of mass? When is it maximum? When he's extended or when he's rolled up? It's greater when it's extended, right? So when is he going to rotate faster? When he's extended or when he's rolled up? When he's rolled up. Why? Can you explain? Yes.
He's just minimizing the distance from his center point.
Right. So any conservations here in this problem? Exactly. The angular momentum of the person, the diver, about which point? There is no fixed point here, so it's going to be about his center of mass is conserved. Right. So So if I were to draw the free body diagram of the diver, what is the only force acting on the diver? The weight, right, which passes through his center of mass. Then it doesn't provide any resultant moment about the center of mass. And there are no couples. So the angular momentum is conserved since MC is equal to 0. Then we get that HC at T2 is equal to HC at T1. We can take T1 to be when he's fully extended and T2 when he's rolled up. And what we're considering here is kind of a planar rigid body motion where what is the axis of rotation in this problem? Where does it point? Into the page or outside the page, so perpendicular to the page, right? Doesn't matter if it's negative. So the angular velocity is along EZ, making a few symmetry assumptions. Then the angular momentum is going to be IC. So if I project this along EZ, I'll get ICCZ omega at T2 is equal to IC dz omega at, T1. And I have to be careful, the moment of inertia is also changing, right? So the product of ICCZ and omega is constant. Since ICZZ at T1 is greater than ICZZ at T2, and this product of I omega needs to remain constant, what does this say about omega at T2? Greater than omega at T1. Does that make sense? Now we're given the angular velocity of the diver at T1, 0.3 revs per second. I can make assumptions to calculate the inertia of the person. What assumptions would those be? Yeah, exactly. At time T1 is like a rod or a rectangular plate. T2, he would be like a disk or a cylinder. The depth does not matter. And then I can calculate the moments of inertia, and I calculate omega at T2. Take a few minutes, 2-3 minutes, finish up this problem. And then let's start looking at problem 2. I'm happy to answer any questions. Questions.
Using the right values. I thought it was a rectangle at first.
You could do rectangular, or the depth will not matter, actually.
I just did a rectangle. I guess it's slender, but it's the same thing.
Yeah. You did not get this same answer? There were extra sets, I think, in the second row. Okay, were we able to get the same answer?
Yeah.
Any questions?
Yeah, we're taking it to be a slender rod or a circular rod when he's in this.
Like, you can take a standard rod or a rectangular parallel. That will not matter. Yeah, if you consider, like, front view, if you consider him to be a slender rod, or like, because any distance like along EZ will not matter, kind of the depth along EZ. Because this and this have the same mass distribution about EZ. Okay, done? Questions?
I have a question.
Yes.
Will we be told on the exam whether or not like the inertia we should use, like for example here, whether or not to use a cylinder or a sphere for the rotational inertia?
Yeah. In the exam, I don't have a correct answer. Whatever answer you have, if it's justified well, it's going to be fine. Questions? Done? Okay. Let's look at problem 2. Wait, I'm going to erase the board. Okay. A uniform slender bar of mass big M and length big L is translating on a smooth horizontal, on the smooth horizontal xy plane with velocity v big M. When a particle of mass small m traveling with a velocity v small m as shown strikes and becomes embedded in the bar, determine the final linear and angular velocities of the bar with its embedded particle. Take a minute, think about it. How do we solve this problem? Okay, so what do we think? Any ideas?
I guess there's a first.
Yes.
I think there's conservation of linear momentum
Conservation of linear momentum for which system?
for the entire system.
Which time?
Before and after.
Right, so during collision, basically anytime the linear momentum of small m and big M is conserved. Why?
There's no external forces.
Well, there are the moments and the normals and the weight forces.
Or they sum to
They sum to 0, right. Correct. Any other conservations? Angular momentum, which system? About which point?
They're connected center of mass.
Right. Why? No external forces, right? The moments, the weights and the normals, they cancel out because there is no motion along EZ, or motion perpendicular to the plane, and the collision force is internal to the system, right? So here we have two conservations. For the combined system of M plus M during collision, F is equal to 0. So So C is the center of mass of the combined system somehow. I think it might be a good idea to add a rotational basis here. Any questions? Yes.
I guess can't we just pick any arbitrary point for angular momentum? Because it should be conserved at any point since there's no external forces.
No. Because, okay, you see the equation about for balance of angular momentum C, and P is equal to H dot P or H dot C plus Archimedes because I'm AC. So even if MP is equal to 0, because the sum of moment is 0 about any point, does that mean that H dot P is 0? Or no, because you have the other terms.
So then the other terms usually expect some sort of acceleration of velocity, right? So if we pick I guess a point that's fixed.
No fixed point.
Okay.
This other term would cancel out if there were a fixed point, which is not the case. Or if you take the P to be the center of mass, which is what we do. Yeah. Any other questions? Okay, so now how do we solve for the motion of the system? The velocity, find linear and angular velocities of the bar with its embedded particle. How do we use these conservations to solve for final linear and angular velocities of the particle with the bar with the embedded particle? What do we do? Yes.
I think you should set up your equations for the sum of linear momentum before and linear momentum after, and the sum for angular momentum.
Right. I will start with these equations basically. G is equal to G prime. So, what is the linear momentum of the system pre-collision? G. Yes.
1/2 big M Vm in the x direction, and 1/2 small m Vm.
Where does the half come from?
Oh, yeah, my bad. It's not energy, it's just no 1/2.
But you're right in saying that the linear momentum of the system is the sum of the linear momenta of the constituents. So basically, big M, V big M, plus small m, V small m. Okay, that's equal to post-collision, the system is going to be combined. So it's going to be one rigid body, mass big M plus small m, and the velocity of the center of mass of that rigid body, Vc prime. So Vc prime, even if I don't know the geometric location of Vc yet, I can say that its velocity is m Vm plus m Vm over m plus m. Oopsie. Okay. Deal? Now for angular momentum. I think I'm going to need the board space, so let's do this. Hc is equal to Hc prime post-collision. Okay. How do I calculate the angular momentum of the system about the center of mass of the combined system C pre-collision? So the system is composed of what? A bar, which is a rigid body, and a particle, right? So I want to calculate the angular momentum of the system. That's also going to be the sum of the angular momentum of the constituents. So what's the angular momentum of the bar about C, the center of mass of the combined system? Pre-collision. It's going to be 0. Because, why is it going to be 0? Yeah, so the center of mass of the combined system just before collision is going to be somewhere here. M is almost at the bar but hasn't touched yet. And omega is not 0 for the bar. So Hc of the bar plus Hc of the particle. Hc of the bar is 0 pre-collision. Now, what is the angular momentum of the particle pre-collision about C? How do we calculate the angular momentum of a particle? You just said it, R cross mv, right? But since it's about C, I'm going to say that R the particle, let me call this point, I'm going to call the center of the bar A, the particle B, RB minus RC cross mass of the particle, V of the particle. Okay? Now, yes?
Sorry, how do we know that the angular momentum of the bar is 0 about the center of mass?
Good question.
Because it's not rotating, the bar isn't rotating, but the center of mass is moving, isn't it? If we take that the combined center of mass of the particle and the bar, like it's kind of moving towards the
right, then our solution to this is to consider the angular momentum of the system just before impact. So directly just before, where C is not moving much. Let me think. If we consider the angular momentum of the bar even when C is still far away from the bar, when the particle is far away from the bar, what happens? Okay. I'm calculating the angular momentum about a moving point. I would be calculating the angular momentum of the bar about C. It would be the integral over the body of the bar of R minus RC cross the velocity of the bar dm. The velocity of the bar would be along Vex. It's constant for all the points on the bar. Okay, and R minus RC for all these points, if it has a non-zero AY component, you will have a non-zero angular momentum. So we kind of have to consider the instant just before, I think. Okay. Any other questions?
Is it not moving just before because the change in the position of the center of mass gets less and less as it gets closer?
Yeah.
I think it's because the velocity is pointed straight at the center of mass when it's about to hit. Because the
I.
like on top of the bar. Well, like the velocity of the bar is going straight to the right, and then the center of mass.
Oh yes, this is right. That's correct. So the velocity of the bar is Vex, which is constant. So when I calculate the angular momentum of the bar, I can R minus RC dm cross Vex. So once this R minus RC on average for all the points becomes along Ex, which this I can write as the center of mass of the bar, which is RA minus RC dm. I can integrate this to that. RA minus RC cross Vex. Yes, when this is along Ex or almost along Ex and the cross product is 0, then the angular momentum is 0. You're right, sorry. Does that answer your question?
We're considering the velocity of the bar, not the particle. Okay.
Yeah. Okay. So, in summary, pre-collision, bar, no angular momentum. Particle, it does. We calculate the angular momentum using the angular momentum of a particle, R cross mv. But here, it's the angular momentum about the center of mass, C, so RB minus RC cross mv of the particle. How do I calculate the angular momentum of the system post-collision? And there are many ways, well, a couple of ways I can think about to do this. Angular momentum of the system post-collision.
Are we actually trying to calculate the angular momentum, or are we trying to use that to work backwards and find the angular velocity?
Yes, the latter.
Because it looks like we have the angular momentum of the whole system by just like adding the two beforehand, and then we know that should be like I omega afterwards.
Right. So for the angular momentum of the system post-collision, I can think about it in two ways. I can think of a new rigid body that is composed of the bar plus the mass added to it, or I can think of it still as a bar plus a mass, a bar and a particle. But now the motion of the particle is constrained by the fact that it lies on the bar. So I can think about the angular momentum of the system post-collision. I can think of a new moment of inertia of the bar plus particle about C omega EZ, or I can think about it as IC of the bar omega EZ plus RB minus RC of the particle cross M V of the particle, which is going to be now at VB prime, where, so that's the angular momentum of the bar plus the angular momentum of the particle, where VB prime is not arbitrary. VB prime is related to the velocity of the center of mass. Omega, the same angular velocity as the rigid body, crossed with RB minus RC. So for the angular momentum of the system, I can do it in two ways. I can consider a new rigid body, the part plus the particle, or I can still consider the two bodies to be separate, but the velocity of the particle can be calculated from the velocity of, from the fact that now it's a material point on the rigid body, right? If I were to use this, IC of the bar plus particle, we know that the angular momentum of a composite body is the sum of the angular momentum of each body on its own. That would be IC of the bar plus IC of the particle. How do I calculate the moment of inertia of the bar about C, the center of mass of the combined system? Tables. Will I find the value in the tables? No, I'm going to have to use the tables and the parallel axis theorem, right? So IC of the bar, what I'm going to find in the tables is the moment of inertia of the bar about its own center of mass, which is IA of the bar. IA of the bar plus the mass of the bar, which I think it's big M, right? Mass of the bar times the distance between C and A times AX squared plus AY squared. Where here RC minus RA okay. Now I have to add the moment of inertia of the particle. How do I calculate the moment of inertia of the particle? Yeah, mass times distance squared. Or I can think about it as using the parallel axis theorem. What's the moment of inertia of a particle about its own center of mass? 0, right? Because the particle has no mass distribution. Plus the parallel axis theorem term, which is going to be plus the mass of the particle times the distance between the particle and the center of mass of the combined system. So I'm going to call plus bx plus by squared, where bx and by are the components of RB, RC minus RB. It doesn't matter if I write RC minus RB or RB minus RC because I'm squaring the terms. Yes. No, during impact or after impact, basically. It's prime. It's when the particle is now fixed to the bar, embedded in the bar. Okay, so in summary, we have this. The particle is colliding the bar. During this collision, we have conservation of linear momentum and conservation of angular momentum. We can use the conservation of linear momentum to determine the post-impact velocity of the bar. And we can use the conservation of angular momentum to determine omega I will call it omega prime, the angular velocity of the bar post-impact. So the linear impulse linear momentum equation gives us Vc. The angular impulse angular momentum equation should give us omega prime. So what does the angular impulse angular momentum equation say? It says that the angular impulse or angular momentum pre-collision is equal to the angular momentum post-collision. The angular momentum pre-collision is 0 for the bar and this for the particle. Post-collision, I can calculate it in different ways. I can either say this or that. What is this? This considers the particle and the bar as a new rigid body, whereas the second equation considers the particle and the bar as two separate rigid bodies. But the velocity of the bar is not, of the particle is not arbitrary. It's a material point. The particle is a material point on the rigid body. Okay, so take 10 minutes, do these calculations, make sure that everything is okay, and let me know if you have any questions. Yes?
The thing I did was I tried to find like an equation for like the position for like the center of mass.
Yes, you are going to need to find the location of the center of mass. You're going to need to find RC, which we use in these equations. Yes?
And I guess I'm kind of confused how it seems to me like the distance, this position of the center of mass would just be for all of our parallel access theorems, it would just be n times that RCM squared, right? Or that position of the center of mass squared instead of ax squared plus ay squared and bx squared plus by squared.
Wait. RC, let me take a point D here. RC with respect to D is going to be equal to the mass of the bar times length of the bar over 2ex plus the mass of the particle times 3L over 4 ex over m plus m. Is this what you did? What did you do?
I summed the position of or the distances of A and B from the center of mass times their masses, and I
But how? You don't know the center of mass yet. So what did you say? MA or A with respect to C plus MB or B with respect to C is equal to 0.
Yeah.
And then you were able to find RA with respect to C and RB with respect to C?
So the way you find the center of mass here is you just treat some point as your like origin.
Yeah.
From there so I think I treated point A as my origin.
And then you have to do algebra.
Yeah, that's fine.
And that's how I got what I got.
Yeah, that's fine. Then if you treat A as your origin, your center of mass would be at small m times L over 4 divided by small m plus big M.
Yeah.
Yeah.
And so that would now be my RC.
That would be your RC relative to A.
RC relative to A, and I can plug that into all of these equations.
Well, yeah, RC relative to A.
Then does RB here represent the vector from B to A? Because I'm treating A as my origin.
No, but RC minus RB is the same as RC relative to A minus RB relative to A. Right? Because that's RC minus RA minus RB minus RA, so minus minus. Yeah.
The vector I just found from A to C minus the vector from B to A.
Yeah. Any other questions? How is it going? You solving the problem?
Go through it.
Any questions? Okay, good so far. How are you doing today?
Okay.
Why are you late to class? Try not to be late. Oh, I'm sorry. What happened? Are you feeling okay?
I'm okay. It's kind of just impacting my sleep, but it's this one ledge that's like outside of my house. Like,
Oh, I'm sorry. Did you get it checked out? Any questions? Sure. Any questions? Questions? Any questions? How's it going?
So we're assuming that right before the center of mass will be the same as right after, right?
Yes. Yeah.
Because it would mess us a lot if we used A as the center of mass before and B as the
Oh no, you cannot. You need to always use the center of mass of the combined system. Yeah. All good? Any questions? Okay. How's it going?
Alright. I found the relative
Okay.
system essentially. So
Okay.
I just plug it in.
Still working to get the final answer.
Yeah.
Cool. Any questions? Good. How's it going? What is it? I didn't hear you, sorry. Do you have any questions? No? Any questions?
in this relative motion equation, this has, doing it this way gives you the unknown omega prime twice, right?
Yeah.
Because it's also a component
Yeah.
here.
Yeah. Yes. And VC prime you already found from the balance of linear momentum. questions? Okay, 5 more minutes and we'll need to jump to the work energy theorem. So, yeah.
This formula. One of the formulas that we use is like R equal IC bar omega prime easy plus RB minus RC cross MBB prime. Would that all work?
Okay, sorry, can you say it again?
So for the middle equation, IC bar omega prime easy.
IC bar, omega bar, easy. Okay, yes.
That one VB prime just VC prime. Would it be that case? Because it's just final velocity? Or VB prime now VC prime?
They're not the same, right? Because there are two material points on the same rigid body, but we know that different points on the same rigid body can move differently. So VB prime is not equal to VC prime. Actually, VB prime minus VC prime, you see the equation just under it? VB prime minus VC prime is omega prime plus RB minus RC. Yeah.
Theoretically, but then apparently with the solution, it's not supposed to be done this way.
Okay, we're going to need to move on to the work energy theorem of a rigid body. So we're going to derive all of these, but let me just introduce it. So to calculate the kinetic energy of a rigid body, we use Koenig's decomposition. The kinetic energy of a rigid body is divided into two components, the translational component and the rotational component. What is the translational component of the kinetic energy of a rigid body? From the board? Half mvc dot vc. And the rotational component is half ic dot omega, or half hc dot omega, or half ic omega dot omega. So the kinetic energy of a rigid body can be decomposed into two components, rotational and translational, which is this. So it's not just half mvc dot vc. That's not right. You have to include the rotational component of the kinetic energy. Okay? Now, in the special case when you have a rigid body rotating about a fixed point, then you can write the kinetic energy as half io omega dot omega. Okay? So in general, the kinetic energy of a rigid body is this. In the special case when there's a fixed point O on the rigid body, you can write the kinetic energy as this, where now the inertia tensor is calculated about O instead of about C. So we will show this. Then the work energy theorem has two forms. Two forms here, and then we can also integrate it with respect to time. So this form is the rate of change of kinetic energy is F dot Vc, the power of the force F, plus the power of the moment. So we previously defined the power of a force. The power of a force is F dot V dt. Is F dot V. That's the power of a force. The power of a moment is the moment couple dotted with the angular velocity omega. So here, these two equivalent forms come from looking at the two equivalent systems. You did this in statics, right? You have a rigid body, you have a distribution of forces acting on it, couples. You can find the equivalent force and moment acting at the center of mass. So the work energy theorem comes from the two equivalent systems. The rate of change of the kinetic energy is the work of all the forces plus the work of all the moments, which for this system is the work of F and the work of MC, and for the upper system is the work of FIVI and the work of the couple moments. So the important thing to note here is that the power of a force is the force dotted with the velocity of the point of application of the force. So remember initially when we defined the power of a force acting on a particle, we said it's F dot V. We didn't have to define the velocity of which point on the particle, because for a particle, it just has 1.1 velocity. For a rigid body, to calculate the power or the work of a force, we have to dot with the velocity or displacement, not of any point, of the point of application of the force. Okay? So for example, if I consider a simple pendulum, like this, a bar pendulum. What are the forces acting on this bar? Weight at the center of mass and reaction force at O. What is the work of RO? 0. Why? It's being applied at a point O with 0 velocity. Okay? To find the power of or work of a force, I have to dot it with the velocity of the point of application of the force. Okay, great. Then I can integrate the work energy theorem, get this, where again, the new thing here is the moment of a couple. How do I calculate the moment of a couple? The work of a moment, the work of a couple. How do I calculate the work of a couple? To calculate the work of a force, remember I integrate F dot V dt or F dot dr. For the couple, I dot the moment with the angular velocity. Then I get the work of the moment. Okay? So let us show these. First, we're going to start with the Koenig decomposition, the kinetic energy. Okay. Kinetic energy of a rigid body. Can anyone guess how we're going to calculate the kinetic energy of a rigid body? How do we calculate the kinetic energy of a particle? Half mv dot v. How do I calculate the kinetic energy of a rigid body? It's not that. How do I calculate the kinetic energy for a system of particles? We sum, right? We sum the kinetic energies of all the particles. Now for a rigid body, how do I calculate the kinetic energy of a rigid body? What is it? Integrate, exactly. I take a continuous sum, which is an integral, of the kinetic energy of each particle. So kinetic energy of a rigid body is the integral over the body of half v dot v. Half v dot v dm. Okay, I need you to help me through this. How do I get there? Any ideas? I'm going to need to introduce VC. So here I have the rigid body, I have the center of mass, and some dm, which has velocity v. And I'm summing the kinetic energy of all the dm's to calculate the kinetic energy of the rigid body. What do I do next? Ideas, ideas, ideas. Yes. Yes, so I'm going to relate the velocity of dm and the velocity of the center of mass because they are two material points on the same rigid body. So Vc or V minus Vc so I will replace half of Vc plus omega cross R minus RC twice. Okay, take a second break with me so far. Raise your hand when you catch up so that I know if we're okay. Okay. Great. Cool. Any questions? Okay. Then I'm going to expand the dot product. How many terms will I get? 4 terms. 2 of them I can combine. They're the same. So I'll get half the integral over the body of Vc dot Vc dm plus half times 2 will cancel out. Half the integral over the body 2 Vc dot omega cross R minus Rc dm plus the integral over the body of omega cross R minus Rc dot omega cross R minus Rc. Yeah. Okay. So I expanded, and it's basically a plus b dot a plus b, a squared plus b squared, and 2ab. What happens to the first term? What is it? What happens to it? Yeah, so Vc dot Vc does not depend on dm. So I can take that as outside. I'll get then the integral of dm, which is m over 2 half m Vc dot Vc. So I have recovered from this term, the first term in my kinetic energy, the translational component of the conic decomposition. What happens to the second term? What is it going to be equal to? Zero. Why? Not quite, but remember, VC and omega do not depend on dm. So I can remove the integral from here, take these two terms outside the integral. And what's the integral of r minus rc dm? That's 0. So this term is 0. So we had the integral here over the body of Vc dot omega cross r minus rc, right? But Vc and omega, they don't depend on dm. So I can take them outside the integral. I took them outside, so I move the integral to here. Then I get the integral of r minus rc dm. And this we showed many times it's 0. You can expand. By definition of rc, you'll get that it's 0. Okay? It's basically calculating the average from the average. Yes?
What happens to the cross product when you pull out the VC and omega?
Nothing, it's still there.
Okay.
Yeah. So instead of having the integral of Vc dot omega cross r minus rc dm, r minus rc dm, I'll have the integral Vc dot omega crossed with the integral. Yeah, and you have to do the cross product before the dot product. So yeah. What else? Any other questions? Okay, now I have to look at the last term, which logically speaking should simplify to have hc omega dot omega or have ic omega dot omega. So how am I going to deal with this term? Yes.
I know you answered this already, but I'm still confused on why RC, R minus RC. Yeah.
Yes, I can show you, but I needed to review this because it's something that you should know by now. The integral of r minus rc dm is the integral of r dm minus the integral of rc dm, right? By definition, the integral of r dm is mrc. And this rc I can take outside. The integral of rc becomes the integral of rc. It becomes rc times the integral of dm, which is also mrc. Yes. Okay. How do I deal with this big term? We're going to use the back cab identity. I'm going to look at this as A cross B dot C. What was the back cab identity again? Back cab. Was it A cross B dot C? Let's double check. A cross B. Actually, we can use a different identity here to deal with this, which is that A cross B, wait, maybe I'll write it up here because we're going to use it. It's going to be A cross B dot A cross B dot C cross D is equal to A dot C B dot D minus A dot D, B dot C. Okay, let us try this one. Okay, what will I get? I should get the integral over the body of A dot C is gonna be equal to omega dot omega. B dot D is R minus RC squared. And A dot D is omega dot R minus RC. Squared twice. dt. Okay. Any questions? Yes? dm, sorry. Okay, right. Anything else? Okay, questions? Let's continue simplifying this term. So I can take an omega outside the dot product. Omega dot the integral of R minus RC squared omega minus R minus RC omega dot R minus RC dm, which this we've seen before. This I can rewrite as omega, that was the integral of R minus RC times the identity tensor minus 1 R minus RC dm omega, dm omega, which becomes basically omega dot IC omega. With the half outside, yeah, forgot the half. Gives us what we were looking for. Okay. This should have a half here. Yes, that's what we wanted, that's what we got. Questions? Okay. So we have a lot still to show. We showed the first conic decomposition of the kinetic energy. What should we do next? Show the special case for the kinetic energy about a fixed point O. Right? Because we can never use equations if we do not know where they come from. So we need to show them, make sure they make sense, prove them. Okay. T half m vc dot vc plus half hc dot omega. If on rigid body, then I can write, if there is a fixed material point O on the rigid body, then I can write Vc minus Vo. What is Vo? If O is a fixed point, 0, right? So Vc minus Vo is omega cross Rc minus Ro. And then I will replace Vc by this. Okay, take a minute, chat with your neighbor, make sure they're okay so far. Any questions? Questions? Yes.
Sorry, if we say fixed, do we mean fixed relative to the rigid body or relative to like absolute warp coordinates?
Always absolute.
Okay.
Yeah. Okay. Questions? Any other questions? Okay. So this here, the scalar triple product, this has a cyclical property. If I have, remember, A cross B dot C, I can write it as I can write it as B cross C dot A, or C cross A dot B. These we can all show. So what I want is I want to get the A outside. So that's going to be B cross C dot A half M RC minus RO cross VC dot omega. There's something wrong. We'll figure it out. Okay. Plus half HC dot omega. Then I should be able to take omega as a common factor. Half HC plus MRC minus RO cross VC omega. And I think this should be equal to HO. So we get half HO dot omega. Hopefully we did not do any mistakes. This matches up with what we previously had for HO. HP is equal to HC plus M. Yeah. Yes, this is correct. Okay, great. So what have we done so far? We've derived the kinetic energy for a rigid body. So in general, the kinetic energy of a rigid body is half mvc dot vc plus half hc dot omega, rotational plus translational component. But in the special case where there is a fixed material point on the rigid body, I can calculate the kinetic energy just by one term, half ho dot omega. Now we want to try to derive the work energy theorem. Where does the work energy theorem come from? It will come from the balance laws. So to derive it, I'm going to start with the kinetic energy, and I'm going to take its derivatives. So I know it's a little bit tedious what we're doing, but I think it's good to know where things come from, and it helps you use them better, like know where the theorem is applicable, what all the terms mean. Okay. So the kinetic energy, so now we're deriving the work energy theorem. The kinetic energy is half m Vc dot Vc plus half Hc dot omega. I will calculate the derivative of the kinetic energy. T dot is half m. Well, if I calculate the derivative of half m Vc dot Vc, I will get m Vc dot Ac. And it will be two terms, right? Plus half, using the product rule, h dot c dot omega plus half hc dot omega dot. Product rule, calculating the derivatives. Now this term I can write as MAC is what? Force F is equal to MAC. So that's equal to F dot VC plus here. Here, if I can show that half HC dot omega dot is equal to half HC dot omega, H dot C dot omega, if I can show that these two terms are equal, then I will get twice H dot C dot omega. And what is H dot C equal to from the balance of angular momentum? What is it? Exactly, MC. So I will get FC, F dot VC plus MC dot omega. Okay, so that's the work energy theorem that we were looking for, right? It's the first form. T dot is F dot VC plus MC dot omega. That's the first form that we were looking for. So it all hinges on this calculation. Now this calculation, there are many ways to do it. I think the easiest way for us right now is going to be using, just write out the expression of HC, calculate its derivative dot with omega, and then write the expressions of both sides and show that they are equal. I will not go through it because it's a lot of calculations, but it is in the notes. So you can show by actually writing down H dot C and omega dot and HC and omega, what those are, going through the calculations, you can show that they are equal. Okay? So in the notes, there's this method, and there's another method which does not use this expansion. Okay. And this gives us the work energy theorem for a rigid body, this form of it. Now to get the second form, now I have that T dot is equal to F dot VC plus MC dot omega. Let me see what F and MC are. F is the sum of forces acting on the rigid body, right? So F is equal to the sum of Fi dot VC. What about the resultant moment C about the center of mass? That's the moment of all the forces plus the couples. So that's the couples, ME plus I minus RC cross Fi dot with omega. So this is equal to, and here I have to add a sum. Okay, so that's the sum of Fi dotted with Vc plus Ri minus Rc cross Fi dotted with omega plus Me dot omega. Are we okay with like the sum of forces is equal to sum of Fi, and MC is the sum of moments about C, which is the moment of all the forces plus the couples. And this second term here, I can also do a switcheroo of the cross product dot product to get that this is equal to omega cross Ri minus Rc dot Fi, which makes that I can take Fi as a common factor dotted with the sum of Vc plus omega cross Ri minus Rc, which, can anyone guess what this term is equal to here? Vi. That's great. Oops. Okay, so now I've shown the two forms of the work energy theorem. The second line is just integrating with respect to time. It's pretty straightforward. Again, how do I calculate the moment of a force? The integral of the F plotted with the velocity of the force dt, or dotted with the displacement of the point of application of the force. And the moment of the work of a moment couple is the integral of m dot omega dt. Deal? We'll try to do a problem right now with whatever time we have left, and you'll do more problems in the discussion section tomorrow. So set 23, last set, I will post some problems for Lagrange's equations of motion by next Thursday. Okay, so the conservation of energy, all the conservative forces, conservative moments apply in the same way they did before for particles and systems of particles. So for example, if I go through problem Problem 2, is the energy of the plate conserved during its motion? Problem 2, a uniform rectangular plate is released from rest in the position shown. Determine the maximum angular velocity omega during the ensuing motion. Friction at the pivot is negligible. Is the energy of the plate conserved during its motion? Yes. Why? But there is a reaction force at O acting on the plate. But it's workless because why? It's acting at a point with no displacement, zero velocity. So the only force doing work on the system is which force? The weight, which is conservative, so the energy of the system is conserved. What about 3? Is the energy of the bar conserved? I heard a yes. What about any other input? Yes. No, why not? But I'm thinking of the bar on its own. For the bar on its own, what are the forces acting on it? The spring force, it's a spring force. This is an extended spring. And the reaction force at O. And the weight. Spring force and weight are conservative. Reaction force at O is workless. So is energy conserved? Yes. Okay, what else do we have? 4 is energy conserved. Yes. Yes or no for 4? Is energy conserved? Yes. Okay, 5. 5 is tricky because 5 is not one rigid body, it's 2 rigid bodies. So the work energy theorem for a system of rigid bodies and particles is the sum of the work energy theorem of each. So here what you have to do is you have to calculate the work energy theorem of A, B, B, C, and then sum them to see if the energy of the system is going to be conserved. Okay? So for the work energy theorem of a system, the work of internal forces does not necessarily cancel out. Okay? I mean, you can think of a spherical robot. There are no external forces acting on the spherical robot, but maybe there's a motor inside that provides energy to the system. So the energy of the system is still not conserved, kind of thing. You have to look at each component separately and then sum the work energy theorem of each component separately to get the work energy theorem of the system. Then you see if energy is conserved or not. You cannot just directly say that the external forces are all whatever, workless or conservative, so energy is conserved. We have to take into account internal forces and their work in the work energy theorem. Okay? This problem 5 has a solution video. Let us go to problem 1. We did this problem before. 2 wheels, shown again here, represent 2 extreme conditions of mass distribution. For case A, the mass m is assumed to be concentrated at the center of the hoop in the axial bar of negligible diameter. For case B, the mass m is assumed to be concentrated at the rim, in the rim. Determine the speed of the center of each hoop after it has traveled the distance x down the incline from rest. The hoop rolls without slipping. Is the energy of the system conserved in this case of the hoop? So it's the same hoop in both except the inertia, moment of inertia is different. Is the energy of the hoop conserved? No, why not? There's friction, but the friction force is being applied where? At the contact point P, the contact point between the cylinder and the ground. What is the velocity of point P? 0. What is the work of the friction force then? 0. So when you're rolling without slipping, is energy conserved? Yeah. You're going to stay rolling without slipping forever. Now, if this disk were slipping, would energy be conserved? If it were slipping? No. Energy would not be conserved. Energy would be decreasing. Decrease up to a point where you get to roll without slip, then the energy is going to be constant. Have you ever played bowling before? You throw a ball, and maybe initially, or even if you're playing billiards, initially it's slipping, and at some point it transitions to rolling. And when it's rolling, it's stay rolling forever, because energy is conserved during rolling. But during the slipping phase, energy is going to be depleted until you get to the rolling. Yes?
Wouldn't because the normal force is perpendicular to the slope, wouldn't that not be, it would have like a component along the direction that the hoop is moving, and wouldn't that make it?
No, the normal force is applied at point P also, which has 0 velocity, so the normal force is workless. Plus it's perpendicular to the motion. Not that it matters. It only matters the velocity of the point of application of the normal. Okay? Yeah, so the bowling ball problem or the cue ball problem is a problem that I've given in final exams before. You'll see it in the previous's. Of a ball or a system transitioning from slipping to rolling without slipping. Okay? So how much time do we have left? 15 minutes? Okay, great. So problem 1 is going to be your quiz. Go ahead, do it. I'm happy to answer any questions. That's a pair work quiz, by the way. You can do it in pairs.
Maths is in the sort of bar, none of it is in for the